Welcome to lecture 19 on risk management and insurance. In this lecture, we consider the normal power approximation to the loss function. Now, the insurance company faces a problem. It may not know the upper tail of the loss function because extreme losses occur rarely. And so it may not have sufficient observations on those extreme losses. Let's go back to the loss function. So we have here the loss x. That's a loss distribution. Now, those extreme losses up here, they are only rarely observed. Now, here's actually those losses here in an intermediate range, they occur quite frequently. So the insurance company observes those losses. It can estimate the loss function here. But up here in the tail, maybe a loss like this, an extreme loss like this, it only observes every 100 years. And the insurance company is only 20 years old. And even if it observes it once, maybe after 100 years, a single observation is naturally not much. So there's a lot of uncertainty about this upper tail. It's not observed. So what the insurance company can do, it can approximate this upper tail with a normal power approximation, and can then use this approximation to calculate the probability of ruin. So the normal power approximation to an arbitrary density function can be used to estimate the probability of a loss outside the range of values that is observed with sufficient frequency. The values out in the tail you observe either never or almost never every 100 years. We don't observe frequently, so we don't know the tail. And you proceed in two steps. First, you take the random variable x, which is a loss. You subtract the expected value, you divide by the standard deviation, and so you get now a new random variable x tile. X is transformed in x tile with a mean of 0 and the standard deviation of 1. That's just a normal normalizations that you use quite frequently and you do in introductory statistics classes. But this random variable x tile is still skewed. It still has a skew, so we have now also to get rid of the skew. And that you can do with a normal power approximation. Then you get a random variable which is normally distributed, which is no longer skewed, also with 0 mean and standard deviation of 1. So we begin here with the loss function. That's the loss function for the random variable x, for the loss x. We normalize that, so we subtract the mean, we divide by the standard deviation. So I'm getting x tile, the random variable x tile. It may look somehow like this. It still has a positive skew. It has a mean 0 and it has standard deviation 1, but it still is positively skewed. And then in the second step, we transform x tile into z, into the random variable z, which then again has 0 mean, standard deviation 1, but is also normally distributed. And that's then this random variable here. Now the second step is done like this. You get the x tile from the first step. That's a random variable with mean 0, standard deviation 1, but still has a skew. And you transform it with this formula, and then you get the z. Now in the expression here, you have actually g Now G is basically given by the skewness, by the standardized third moment. So you calculate this G, you plug it in here, and then you get a random variable set. And that one will be normally distributed. So you can actually now use the tables for the normal distribution. And you can use it then to determine the probability of ruin. Now here just a reminder, in case you're a bit rusty. So the third moment measures the skewness of a distribution. A positive skew, then you have this thin upper tail. A negative skew, then you have this lower tail here, okay, which goes this thin lower tail. Now what we do, we use the standardized third moment, that's the third moment, but we also divide by the standard deviation to the third power. So you see, I divide here by the standard deviation to the third power. So different distributions are not distorted by differences in dispersions. So this then actually takes account of the dispersions. It's a standard deviation to the third power here. So for the normal power approximation, we need to know three parameters. We need to know the expected value, the mean. We need to know the standard deviation, and we need to know the skewness. Let's go back to the loss function. So here in this intermediate range, you know the loss function, and with this information, with those observations, you can calculate the expected values, the mean loss, you can calculate the standard deviation, and you also can calculate the skewness. And then you use those three parameters to make the approximation here for the upper tail here, which you never observe. So basically what we do, it all depended on those three parameters that you have estimated, the mean, the standard deviation, and the skewness. Now, if you have a bad estimate of the skewness, then naturally your approximation here up here will be bad. Basically, you project what you have here, you project it into the tail. And if your estimate of the loss function in this intermediate range here is bad, if the parameter, particularly if the parameter for the skewness is not a good estimate of the true skewness, then naturally your estimate of the tail will also be bad. Your approximation of the tail will also be bad. So be careful about this. So let's make an example. Let's assume we have now this information. We know the expected loss. We got it from those data on the loss function from the intermediate range. We got the standard deviation. We have an estimate of the skewness. And let's hope those estimates of those three parameters are good. Now let's assume we have an initial amount of capital of 100 million. The expected loss is 30 million, the standard deviation is 10 million, and the skewness is 3, and we would like to achieve a probability of ruin of 0.1% or less. Now, will this really produce? Are the available funds sufficient? Are those $100 million sufficient to achieve this desired probability of ruin? Now, if you look at it, you see we have $100 million. The expected loss is only $30 million, and the standard deviation $10 million. So we are 7 standard deviations away. So we have here a buffer of 7 standard deviations. And if it's a normal distribution, then you don't have to go to the table. It's very unlikely that the random variable is 7 standard deviations away from its mean, from its expected value. You have to go to the tables if maybe you are 2 or 3 standard deviations away from the mean. But with 7 standard deviations, that's very, very unlikely to happen. So it's very unlikely to happen that we will run out of funds here. We have an expected loss of 30 million with a standard deviation of 10 million. But our funds are 100 million, so we are 7 standard deviations away from it. And so if it's a normal distribution, okay, then you would say it's fine. You don't have to do any calculation. But we have here a skewness. We have this thin upper tail. Our distribution is skewed. So with a small likelihood, we will have very huge losses. And this natches can really use up our funds here. So read this, that's what I said before. So available funds exceed the expected loss by 7 standard deviations. And so with a normal distribution, there would be no need for further analysis. But our loss function here is skewed to the right. And so we really have to check it out, because there is a small probability that we have a huge loss. And so maybe those $100 million of funds will be used up. So the question is, do we still have a maximum probability of running of 0.1%? So let's do first step 1. The random variable is here the amount of funds. So let's put the amount of funds equal to X. That's $100 million. And let's normalize it in the first step. So 100 million minus 30 divided by 10. So we are 7 standard deviations away from the mean. So that's what the normalization shows. So I'm going to, but this new random variable here, X tile, it has now mean 0, standard deviation 1, but it still is actually skewed. So I cannot use the table here. So in the second step, we get rid of the skewness. So calculate the G. So the standardized skewness, remember that G, okay, is basically standardized skewness divided by 3 faculty. So you have 3 divided by 3 faculty here. That gives you 0.5. And you plug in those 0.5 for the G in the formula. G is here, here, and here. And you will get a value for the random variable set of 3. Now, this random variable set has a normal distribution. And it also has mean 0 and standard deviation of 1. So since the set has this normal distribution, the probability that it will be bigger than 3 is only 0.00135. You see we got here 3. Now, the probability that we have now a set value that's bigger and that we will exhaust our funds, the $100 million, we can now look it up in the normal table. So we could use the table here from the Zweifel and Eisenbuch, but you can actually also use Excel or the spreadsheet, the programs that they are using in South Africa. So it's 1 minus the normal distribution up to the point to 3. So what's out in this tail? Okay, that's out there. 0.00135. Now, when you use the Zweifel and Eisen table, don't forget this 0.5. The table gives you only the right side of the normal distribution. So you also have to add here then the left side. And then you get also 0.00135. So the probability of ruin is 0.135, which is very low, but it's more than the required 0.1%. So here I express this again in percent, so I'm getting rid of those 0, 0. So even if here we are now 7 standard deviations away, we have a buffer stock of 7 standard deviations. The expected loss is 30, standard deviation is 10. So we are 7 standard deviations away from the mean. So it seems to be a lot of capital, but we do not achieve this ruin, the probability of ruin. It will be a little bit higher, and that's because the distribution is skewed to the right. With low probability, we will have huge losses. And then we exhaust here this capital. Now you can also calculate the minimum equity capital that is required to get a certain probability of ruin. That's the reverse calculations. Before S was given the capital, it was $100 million. Now let's calculate that S value. So we go to the reverse transformation. We go from the Z variable to the X variable. So first transform the Z variable into X tile. That's done by solving equation 12. So here equation 12, from the Z variable, we would like now to know the X tile. So solve this equation here for the X tile. Okay, that's not so easy, but here we have a solution. And then when you have the X tile, then transform this back into the X variable, into the amount of capital. So that's very easy. Then you just solve equation 11. So X tile is now given, so solve this for X. So just rearrange this equation 11. So here, in the initial problem, what we were given was the capital, the expected loss, the standard deviation, the skewness, and we wanted to check whether really we get this probability of ruin. And we saw it will be actually a little bit higher. Now we are looking for the capital. The capital is not given. We know the expected loss, the standard deviation, the skewness. We also have the probability of ruin. We will now ask how much capital do we need? And it's just a reverse problem. You are given the Z, transform it into the X tile transform it to the X. The X is the capital. So let's assume again in the example, the expected loss is 30 million, standard deviation 10 million, skewness 3. And let's now work with a tiny probability of ruin, 0.025, much less than 1%. So how large must this initial capital be, S, to achieve this required probability of solvency of 99.975%? This amounts to a required probability of solvency of more than 99%. So the random variable set will exceed 3.48 with a probability of 0.025%. So it's 3.48. Again, you get this from Excel. You take now here's an inverse of the normal distribution, and you have actually to give in the 9975. You don't give in the 0.025. This gives you 3.48. That's out in that's the critical value, and out in the tail you have now just 0.025%, or To the left, you have 99.975%. Again, you could use the table. So you take this 348, you plug it in. So take the 348 here for the set. That's its critical value for this random variable. And the tail will be then less or equal to this value here. If you have this critical value here of a set, 3.48. This gives you the x tile, and then you have the x tile and solve it for x. So you have the x tile here and plug it in here, and you get the x. So you need 120 millions of capital. Then the tail will be this or less. And the probability of solvency will be very, very high. So a probability of solvency of 99.975% requires $120 million of funds. So for example, if your initial capital at the beginning of the year is 80 million, then your premium income should be 40 million. So I just make here an assumption. Let's assume we have 80 million at the beginning of the year. Then you need an additional 40 million, and that you get through the premium income. That's a premium income that you have to charge. And this will require a safety loading of 33.3%. Here you just use equation 1 from the very beginning in this chapter. Just solve it for lambda for the safety loading. So the premium income would be 40. Then 30 million would be the loss. Yeah, that's expected loss. And okay, you get here a safety loading of 0.333 of 33%. Okay, this finishes this lecture. So we had here a very interesting problem in this lecture. You see, in probability theory, we have all those probability distributions, and we would like then, we are particularly interested actually sometimes into the tails, into extreme events. That's what we would like to avoid. So we would like then really we worry about the probability of ruin here in insurance. And the unfortunate thing is those tails basically we don't know, because you almost never observe them. So the tails happen very, the events happen very, very rarely, maybe every 100 years. And so maybe you can approximate the tail, but it's not without problems. You see, you estimate here for the intermediate range, you estimate the mean, you estimate the standard deviation, you estimate the skewness, and then you assume that those estimated parameters also just apply out here in the tails. Now, whether that's correct, okay, that's really debatable. But that's the only thing here that what you can do, and it stands this way. Okay, so thank you very much.